So today we're going to look under the hood to see how a computer can take your instructions and turn them into useful data, and take your ideas and turn them into money. Now, software development, or the idea of programming a computer in order to make an application, is a fast-growing industry, right? There are lots of jobs, and kind of worryingly, people say that we don't have enough college students learning how to program in order to fill all those jobs. What that means is that our software companies may be hindered by the lack of human resources available to them. Now, this is maybe bad for tech companies, but at the same time, if you have the skills to actually program computers, it can be very lucrative for you. But before we get into all of that, we need to actually see how a computer takes your instructions and processes them. So how does a computer even know how to follow instructions in a program? Well, to answer that question, we have to start with the hardware responsible for responding to all of those instructions, namely your CPU, or central processing unit. That's the piece of hardware inside your computer that actually executes instructions. Now, the way it does that is that it works with other bits of hardware in your system. We've already talked about RAM in the past. That's memory. Whenever you load an application or start an application, that application is moved from your hard drive into RAM so that it runs faster. RAM is much, much faster than your hard drive. However, RAM is still slow compared to the CPU. And so for commonly used instructions and data, we actually store that on the CPU itself in something called cache. Now, on a modern processor, there may be multiple layers of cache. You may have level 1 cache, level 2 cache, level 3 cache. The idea is that with each level of cache, you get less memory, but it's super fast. It keeps getting faster and faster. So the most used stuff might be in level 1 cache. Very, very fast memory, but you don't get very much of it. Now, as fast as cache is, it's still not fast enough to keep up with the CPU. And so there's actually memory locations on the CPU called registers. Those registers are where data has to be located, data and instructions have to be located in order to be processed by the computer. Now, we're simplifying things here, so we're not going to talk about instruction registers or program counters or anything like that. But I just want you to kind of get a sense for how things work. Registers are sort of the working space for the CPU. It's where it grabs information in order to process it. Now, once information is in a register, we actually have to figure out what you want to do with it. And the control unit is sort of the central part of the processor that handles interpreting what your instructions are based on the instruction set for that processor. And then based on that, it can know where to send data down different pathways. Those different pathways will do different things to the data, like addition or multiplication. That actually happens in something called the ALU, the Arithmetic and Logic Unit. It's got lots of different data pathways, and depending on where you send the data down, you'll do different stuff to it. Now, all of this gets put together into what we call the machine cycle. So this hardware in your CPU works together to sort of do this 4-step process. First, you have to fetch instructions, then decode the instruction, then execute the instruction, and store the instruction. All right. The fetch process involves taking an instruction either from cache or from RAM, if it's something that's maybe not as commonly used, and putting that information into the registers on the processor for execution. Once it's there, we go into the decode process, where the control unit looks at the instruction to determine what it is you want to do with it. Do you want me to store this somewhere? Do you want me to multiply these things together, etc.? Now, once that happens, then you actually send the data to the ALU. The ALU actually does the work, whatever it is, multiplication, addition, storage, operations, things like that. And then afterwards, you store the result of that operation back in a register. All right, so that is sort of the cycle of where you're sending stuff. Now, once that information is in the register, you might do something else to it. And so now we're going to send it back into the control unit, etc. But the information is sort of flowing in this way in your computer all the time. In fact, if you look at a clock cycle on your processor, most processors nowadays are around 3 gigahertz, which means that if you picture the clock cycle as being sort of the beat of a drum, and with each beat of that drum, data is processed. That means the drum is beating 3 billion times a second. You are performing 3 billion different actions every single second. Now, if you look at our machine cycle, it has 4 steps. So it would take 4 beats in order to actually complete one single instruction. Now, that is still really fast. I mean, you're almost at 1 billion instructions per second if you were to go at that speed. But we can actually do better than that. And processors for a long time have done this. It's a process called pipelining. And so if you think about pipelining, an analogy would be to think about an automatic car wash. When you go to the car wash, you don't actually have to wait for the first car to be completely finished and out of the car wash before sending in the next car. The only limitation really is that you can only have one car at a stage at a time. So you can't have 2 cars being washed at the same time because you only have one, wash area of the automatic car wash. But once that car has left the wash and has moved on to the rinse, well, then you can move another car into the wash area. And by doing that, you end up creating this sort of staggered appearance, right? This is pipelining. Each clock or each instruction kind of gets loaded in one after the other. And so the first instruction starts its fetch process and then gets moved to decode. Now, while it's in decode, a second instruction starts its fetch cycle. And then one moves on to execute, one moves on to decode, and then you start a fetch on a new instruction. And with this process, you can actually get 4 whole instructions as well as partial bits of another instruction, or actually a couple other instructions, all done in 7 clock cycles. It makes the process a lot more efficient. And by doing that, we can essentially say that with each clock cycle, you're actually achieving a full instruction, right? There's a clock or a machine cycle being finished with every clock cycle in this pipelined process. In fact, you can even have more if you've got multiple cores, but let's keep it simple for now. And while that's fine and dandy, but it doesn't really explain how you get your instructions, your ideas, into the computer in the first place. So now we know how the CPU handles instructions. How do we actually give your computer instructions to make an actual program? Well, this is a machine instruction. This is something that a machine might understand. It consists of 3 different parts. One would be the actual, we call it an instruction opcode. This is the thing I actually want you to do to the data. Let's say addition or multiplication. The second part is where the first number, let's say it's multiplication, where the first number is located that I want you to multiply. What register, right? Now, to make things simple, to make things smaller, I suppose, we actually use that same register that we grabbed the first input from, and we often use that as the destination that we're going to eventually send our answer when we're done. But that's just a way of sort of duplicating the amount of information just in that simple machine instruction. Now, the last one is the second register, right, where the second number is located for the multiplication or addition or whatever process we want to do. It's all written in binary based on the instruction set for a particular CPU. And that's a machine instruction. Now, machine instructions are in binary. It's really hard to write in binary. But believe it or not, when computers first came out, we actually did pay people to sit in big rooms and flip switches in order to program computers using binary, using these individual switches of ones and zeros. However, as things went on, we found a better way. We created something called assembly language. Now, assembly language has kind of words, right? But each of those words represents a particular binary code. It's a one-to-one relationship. This word is sort of translated directly into that portion, that binary portion of the machine code. But now I can kind of say something that maybe makes a little bit more sense, right? I want you to load into register 1 whatever is in the memory location 1024. And then I want you to load into register 2 whatever is in memory location 1028. And then I want you to multiply whatever's in register 1 by the number in register 2 and put the answer back into register 1. And then I want you to store register, whatever the contents of register 1 is, the answer from our multiplication, and put that into memory location 1020. So in this way, you can kind of see like, oh, I get it. It's just binary. We're just converting it from binary into these symbols that maybe make a little bit more sense to us. Now, how do we do that? We do that using a compiler, all right? A compiler just converts assembly into binary machine code, just converts those word symbols that we use into the binary symbols that the computer uses. Now, you can see the little note at the bottom. Technically, it's a part of what we would call a compiler, sort of generally called the assembler, but we don't need to get too much into the details here. Now, machine code is almost impossible to write code in, right? If you wanted to do a program that did anything significant, to do it in machine language would just be, near impossible. Assembly language is better, but it's still really hard to write code in assembly. And so we need to find a better way. We already know that compilers can convert one language into another. So what if we just set up a compiler that could convert some other language, a higher level language, something that's closer to English, into assembly, and then that could be converted into machine language. High-level languages that use English-like words were invented in 1957 by Rear Admiral Grace Hopper, a woman who is at the center of a lot of sort of early computer research and design. And she created a language called COBOL. Now, Fortran existed before COBOL, but it didn't use English-like words and a sort of English-like structure to language. COBOL was sort of the first language to have sort of a higher level syntax, something that would sound like a normal language. Now, there are lots of high level languages at this point. COBOL, one of the oldest, BASIC, Pascal. There are a number of C languages that have all sort of derived from the original C language. Java, Python, Ruby, PHP, and there's more that I don't have listed here. There are lots of high-level languages, and all of them kind of work differently, like other languages in the real world, right? Your syntax is different in each of these languages, and so it makes some languages perhaps better for certain tasks and not so good for other tasks, right? The idea is that eventually you kind of find your niche, where it is you want to work, maybe at a particular area, and you have to use those languages. For instance, if you want to program applications for the iPhone, you would do that in either Objective-C or a new programming language created by Apple called Swift. If you wanted to program stuff for Android, well, most Android developers can use Java and to a lesser extent, C++. If you want to produce stuff for the web, well, PHP, Ruby, and Python are all great choices for website applications. And so once you find what you want to do, usually there's a language that's sort of easiest to do that in. Now, compilers, sort of in the broad sense of the term compiler, also allow you to do stuff like link and load common libraries. This is code that's already been written and done. When I want to create a window in Windows, I don't want to have to figure out how to actually draw a window on the screen. Instead, Microsoft has created a library, and I can simply access that library, or what we would call an API, an application programming interface, and say, hey, Windows, give me a window. I want it to be this big. Right? I want it to have these features. And Windows will kindly do that for me. There are lots of libraries out there. Most of them are pretty basic. You probably haven't heard of them, but there are some that are really large and do something sort of specific, and you might have heard of them. Oftentimes you'll have to, download the new DirectX drivers. That may be something you've seen on your computer in the past. But what is DirectX? Why do we use DirectX? Well, DirectX is a graphics library. It contains lots of functions and methods that allow you to create 3D graphics on the screen without having to figure out all of the math and science behind how that stuff should work. And so DirectX, as a result, is used to create most of the popular video games that you play if you happen to play video games. And so DirectX is something that you may have to upload from time or download from time to time and upgrade. So some of these libraries are already there. If you want to become a programmer and you want to, let's say, work in video games, you don't have to go through the process of trying to figure out the math behind how water should react when you walk through it. The person who figured that out probably has a PhD, right? It's much easier to just use libraries of code where that information has already been figured out. No need to reinvent the wheel. So here is sort of what our general idea of a compiler does. We take some sort of source code, something that you've written in a higher level English syntax-like language, like C++. It goes through a preprocessor, which you don't have to worry about, that will sort of modify the code and do some stuff to kind of make it easier for you to write. Then that compiler will convert that source code into assembly. An assembler will then convert that into machine code, and then a loader and linker will grab library code, stuff you refer to in your program but didn't actually write, and put that all together to create an executable binary. This is the thing that you put on a disk and sell at Best Buy, or that you offer online as a download in exchange for money. It's something that hopefully has value. And so where do you fit in all this? You just write your code in that language using a text editor. There are not very many industries, I think, in the world where you can create something that has value based on just an idea in your head and the ability to write in this different language. To write in code that the computer can understand so that the computer can create something that can be copied very easily without any additional costs, but something that has value to people. And maybe, you won't write the next Photoshop, but if you write the next Angry Birds, if you write something that is worth 99 cents to millions of people, it can be a very, very lucrative and wonderful industry to be a part of. Now, I'm not trying to oversell this, and I know that a lot of you are not going to be interested in computer programming as a career. But for those few of you out there who are thinking to themselves, you know what, I can kind of find this stuff interesting, and I think that if I really applied myself, I might be good at it, then do yourself a favor and take the next step. Just take a basic intro to programming class. See if you actually do like it, if you really could be good at it if you put forth the effort. Because if you do, it may be the best decision you make in college. And even if you decide later to not actually pursue computer programming, it still looks awfully good on a resume.